Calculating power factor correction. What we're going to look at in this presentation is how we actually do the calculations and how power factor correction is utilized. It's working with a parallel RLC circuit. That is the premise of power factor correction. We have a parallel RLC circuit. And what we're going to be doing is looking at the circuit at two distinct times. One is going to be before power factor correction, which we will abbreviate as PFC. And then we're going to look at the circuit after power factor correction. So this particular circuit here, 120 volts AC, 12 amp motor, power factor of 0.7. So the first thing we want to do is kind of break down all of the particulars of this circuit before we do any sort of power factor correcting. So the first thing we do is, well, let's look at the values of current and power and watts and VARs. So I'm going to list out the totals for this particular circuit here, S total. I'm also going to do Q total and P total and I total. So right now, all that we have in the circuit is a 12 amp motor, and therefore the total current that we have is of course 12 amps. Now, when we look at the P and Q and S, really what we're doing is we're breaking this object down as a series component, because we know a motor is really a resistor and an inductor connected in series. So what does that mean? It means we have to calculate the value of power, VARs, and VA as a series branch. And so what we end up with for a series branch is the triangle that looks like this, power factor of 0.7, and I can calculate some of these values very quickly. Remember, what's the voltage across the motor? It's 120 volts. So if I wanted to know the total VA of this motor, total VA, then I need to know the total voltage and the total current. So 120 times 12. 120 times 12 gives me 1440 VA. So what's the total VA of the circuit? 1440. At this point, I can use my VA with my power factor, and I'm using a little bit of trick here. Remember, at this point, you should probably understand that you can take this value, multiply it by the power factor, and get your horizontal component. So 1440 times 0.7 gives me 1008 watts. So that is my power. And then finally, Q, I can use Pythagoras. So I'm going to do 1440 squared minus 1008 squared, square root my whole answer, and I get 1028.36. $1028.36. So I'm going to put that here. VAR. All right, so now I have all of the values of this particular circuit before power factor correction. And so when we say we're going to power factor correct, we have to be given some information. So I'm going to say that we are going to power factor correct this circuit to unity. To unity. So what that means is we want a capacitor connected onto this circuit so that when I close the switch, the capacitor provides all of the out of phase current for the motor. So how would we then calculate that? Well, when we are looking at before versus after, there's one key piece of information that we will always transfer or take with us to the after or new calculated value, and that's right here. The watts. The watts of the motor are not going to be affected by the application of a capacitor. And that's because the capacitor has no watts itself, and it won't have any effect on the actual running of the motor. So after power factor correction, what we're going to start with is our power triangle and with a known value from the previous circuit, 1008 watts. Now, in my example, what I've just stated here is I want to correct this to unity power factor, and we all know that unity means a power factor of 1. So if I want a power factor of 1 in my new circuit, that would mean that the total VARs and the total capacitive VARs, so inductive and capacitive VARs, would have to be equal. So if they would have to be equal, that means that I now know how big my capacitor VARs need to be. Take a look over here. The entire inductive VARs are 1028.36. So 1028.36 VAR. That means if I want to power factor correct this to 1, that this must also be 1028.36 VAR. And the reason I know that is because the net outcome of this must be 0 VAR, because we're power factor correcting to unity. So what does that mean? Well, it means that I will now have a 1008 total of VA. So with this information over here, it would be possible for me to work out the size of the capacitor, right? The size of the capacitor is going to be a product of the voltage across it and all the other items. So could we work out, we already know what the Q is of the capacitor. We know what the voltage is across the capacitor, the current of the capacitor, the XC of the capacitor, and finally, what about the capacitance of the capacitor? Could we not work all of those items out now that we know what the VARs is? Then for sure we could. So 1028.36, that would be the VARs. The voltage is in parallel. If it's in parallel, that means 120 volts. If I want to know the current, well, this is a simple calculation with my power. 1028.36 divided by 120 gives me 8.56 amps. That's how much current the capacitor is going to draw when I throw the switch. What about the XC? How many ohms is it going to be? Well, let's take 120 and divide it by the current. That's Ohm's law. 120 divided by 8.56 gives me 14.01 ohms. And then could we work out the capacitance in farads? Yeah, we certainly could. So how large a capacitor do I require? Well, remember, C is equal to 1 over 2 pi FC. So let's say we're using the typical North American standard source, which is 60 hertz. So that would mean I can take 1 divided by 2 times pi times 60, and then we're going to multiply it by our XC. Forgot the X in there, XC. So times 60 times 14.01. Close bracket equals, I have a capacitance of 0. So I'm going to write it down here, 0.000189 farads. So if we wanted to put this into a more common form, we would move the decimals 6 places. 1, 2, 3, 4, 5, 6, 189 microfarad. That would be the size of the capacitor required. So we worked out everything to do with the capacitor just there, but the capacitor aside, I mean, we worked out originally what are S total, Q total, P total, and I total. And we've worked out everything except for I total. So what would the I total be of this circuit after power factor correction? Well, again, the total current is made up of the total VA and the total voltage, 120 volts. So that means if I were to take my S total and divide it by my E total, we should end up with the total current. And so with this situation, the total current we end up with is equivalent to 1008 divided by 120 gives me 8.4 amps. So what we should see every single time we do power factor correction is that the current should get smaller. The current should get smaller total. Keep in mind, when I throw the switch, the motor doesn't know any different. The motor doesn't care. The amount of current the motor draws doesn't change. The power factor of the motor doesn't change. The only thing that changes is where the motor is receiving the out-of-phase VARs. It receives it from this side instead of currently receiving it from this side. So remember, power factor correcting has no effect whatsoever on the item that we are correcting. The only difference it has is on the current value right here, the total current. Let's take a look at one more example here. And this time we're going to calculate it based on not a straightforward, simple, 100% power factor correction, but we're going to do a portion. So let's see what that looks like. We'll choose, again, a source voltage here of 120 volts and 60 hertz. We're going to have a motor. And the motor is going to have a switch with a capacitor because we're going to do some power factor correcting. We don't know the size of the cap yet. We're going to work that out. So my motor is going to be 50. No, let's keep it small again. We're going to make it 20 amps. And it's going to have a power factor of 0.4. 20 amp and a power factor of 0.4. So we're going to divide our little diagram in half here again. Over here, this is going to be before power factor correction. Over here, we're going to have after power factor correction. So let's start on this side. Before power factor correction, S total, Q total, P total, and I total. Well, I know the I total is 20 amps. So before the switch is closed, 20 amps. And when we look at the S total of this circuit, S total is the equivalent calculation of 120 times 20. 120 times 20. So that means that 120 times 20 should give me the total VA. So we got 2,400. Now, let's look at the power factor. If I take the VA and we multiply it by the power factor, that should give me my watts. So 2400 times 0.4, 960 watts. And then finally, we can work out the Q, and Q, I typically use Pythagoras. So 2400 squared minus 960 squared, square root the whole thing, and we end up with 2199.63 var. All right, so out of this information that we've calculated, what item am I going to take with me to the other side initially? Well, this one is not going to change, is it? This is not going to change. We are going to use that. But also, we're going to use the VARs, but we're going to use it in a different way this time. So in this circuit, after power factor correction, this time we want to power factor correct it to a more reasonable value. Power factor correcting to a unity power factor is unreasonable for the cost associated and the possibility of going into a leading power factor if lagging loads are turned off. So instead, we're going to power factor correct this to 0.91, and 0.91 lag. So we continue to be in the lagging portion. So what we need to look at then is a few different items. First thing, I'm going to draw my new after power factor correction triangle. So it's going to look like this. I've got 960 watts, and it's going to be a little bit lagging, right? It's going to be a little bit lagging, so I'm going to draw it a little bit bigger. So it's going to be down like that. Just had to make it bigger so that I didn't actually run into my 960 watts. So this is my power up here. And over here would be Q, right? What's the power factor of this new circuit? The power factor is 0.91. We were told that at the very beginning. So we have to be told this. So 0.91. So if I know what the watts are, and they've given me a power factor, can I utilize my trig and simply calculate what the hypotenuse is? So remember, cos of your angle, where should we write this? Let's write it down here. Cos of your angle is equal to the adjacent divided by the hypotenuse. I know the adjacent, and I know this. I'm looking for the hypotenuse. So that means that we need to take this equation and adjust it so that hypotenuse is alone as a single variable. And that means adjacent divided by cos of the angle, which really means the watts divided by power factor. All right, so let's take our 960 watts and divide it by 0.91. It gives me a new VA here, a new VA of 1054.94 VA. Let's now work out what the net VARs is going to be here, because there is going to be a leftover VARs, isn't there? We haven't fully power factor corrected to unity, and because of that, we are going to have some net or overall VARs. So I'm going to do Pythagoras, 1054.94 squared minus 960 watts squared equals, I'm going to square root the whole thing. It gives me 437.38 VARs. And what would those VARs be? Those would be lagging VARs, wouldn't they, right? Those would be lagging VARs because our power factor here, they've told us we want it to be 0.91 lag. So then how do we work out the size of the capacitor? And it's actually quite a simple procedure. What we need to do is take the old VARs, which were 2199.63, and we're going to subtract off the new VARs. And the new VARs are 437.38. So we're subtracting these two values. The value that we then are left with, the product of that, 2199.63 minus 437.38, gives me the size of the capacitor. Whoops, you couldn't see that. So what we're left with is the capacitor VARs. And that would be the required leading VARs in order to make this circuit possible. And so we end up with 1762.25 VAR. How large is that capacitor? 1762.25 VAR. And so we come to our answer of how big a capacitor do we require? Well, we just calculated it. And finally, with all of this information, let's not forget what's kind of the purpose here. We want to work out how many amps. What's the new current going to be? Well, before power factor correction, we had 20 amps. And we calculated the 20 amps from the total S and the total voltage. So if I want to know what the total current is after power factor correction, I need to know the total VA and the total voltage. So total VA is 1054.94. That means I total is equal to 1054.94 VA divided by 120. So use our calculator. 1054.94 divided by 120 volts gives me 8.79. That's quite a vast difference in magnitude, isn't it? I mean, really, we've gone from a motor drawing from the supply authority 20 amps to a motor that draws from the supply authority only 8.79. So remember, is the motor, the actual rating on the motor, has the motor current rating changed to 8.79? No. The amount of current that is flowing when the switch is closed is changing at these 2 points. But the current that flows through the motor is not changing at all. The current that flows through the motor is still 20 amps. It still operates at a abhorrent 0.4 inductive power factor. And the capacitor is now providing that out-of-phase current, which we could calculate further with this value of VARs here, the capacitor VARs, right? The capacitor VARs will allow us to work out all of those other values. Just for excitement, because I know loads of excitement with power factor correction, let's just complete the final calculations with this capacitor. So we said we had a 1762.25 VAR cap. Let's list all of the variables relevant to the cap: Q, E, I, XC, and finally C. So Q, the VARs of the cap, a 1762.5, right? That was the VARs. Voltage, 120 volts. If I use my power formula, VARs divided by voltage, VARs and voltage gives me current of the capacitor. So 1762.5 divided by 120, 14.68 amps. So this capacitor is going to be drawing 14.68 amps. XC, well, let's use our Ohm's law. 120 divided by 14.68. 120 divided by 14.68 equals 8.17 ohms of capacitive reactance. And then finally, can we work out the capacitance in farads? For sure. Let's take 1 divided by bracket 2 times pi times 60. times 8.17. Close that bracket, and we're left with a really long number, 0.0003246 farads, which when we convert it into microfarads, being 6 decimal places to the right, gives me 324.6 microfarad. So that is our full power factor correction calculation. Try out some of the handouts that I have provided within the course structure, and take a look at how that current value changes depending on how large a capacitor we put in there.